I welcome all of you to the video lecture series on fluid mechanics. This lecture is on topic 1 on introduction. The title of this lecture 5 is Conservation Laws and Associated Variable as well as Term. This lecture is focused on conservation laws and the variables as well as terms which are associated while applying the conservation laws. Let us start this question with a whiteboard presentation. There are two conservation laws which appear in fluid mechanics. Mass conservation law, which states that rate of change of mass is equals to 0. Mass can neither be created nor destroyed. This you can apply for a solid as well as a fluid element. The second momentum conservation law is basically the Newton's second law of motion. It states that rate of change of momentum of a fluid element is equals to the force acting on the fluid element. Now I'll present the variables which are associated while applying the mass and momentum conservation law. This is just an introductory lecture where I am presenting this variable and later on I will present certain associated terms. A much more detailed discussion will be presented later on in the later topics of this lecture series. When you apply mass conservation law, you encounter two variables. They are expressed here in as capital M. But there are two types of M which I am showing you. This is what I am calling as curly M, and this is used to represent mass. This straight M, this I am using to express it as a mass flow rate. Similarly, while applying the momentum conservation law for a fluid element, the terms which are introduced are the product of mass and velocity, which is a vector. So all of you know that the product of mass and the velocity is momentum. Similarly, if you take the product of mass flow rate and the velocity, we can call this as momentum flow rate. Mass flow rate, momentum flow rate. Sorry, this is the momentum and this is the momentum flow rate. I would like to draw your attention that if you compare the course on thermodynamics with fluid mechanics and also with the heat transfer, in thermodynamics also you study mass, but the mass flow rate is introduced in fluid mechanics course only. In thermodynamics as well as heat transfer course, you study heat, but there is a difference. In thermodynamics, you study amount of heat, and in heat transfer course, you study rate of heat transfer. So what I'm trying to emphasize is in thermodynamics, you study amount of mass of the substance or the amount of heat transfer. Whereas when you study fluid mechanics and heat transfer, they are called as rate process. So it's the same variable, they are expressed in terms of rate. Like mass is expressed in fluid mechanics as mass flow rate. Amount of heat which is used in thermodynamics, when it comes to heat transfer course, it is a heat transfer. So these are the associated variable while applying the mass and momentum conservation laws. As I had mentioned, these are the variables: mass, mass flow rate, momentum, and momentum flow rate. Notice that the mass and momentum, they are directly proportional to the volume of the fluid element, whereas mass flow rate is proportional to the surface area. Just to give you an example, if you consider the volume, the mass of air in the room where you are sitting, the mass of the air in the room is directly proportional to the volume of the room. Whereas if you consider the air which is entering from outside to your room through windows, then the mass flow rate of the air which is getting transferred from atmosphere to your room is expressed in terms of surface area of the window, not the volume of the room. So whenever we express in terms of rate basis, you notice that instead of volume, In mass flow rate involves surface area. So if you compare these two expressions, there is an additional term which I have intentionally not showing you. This is to make you realize the expression for mass flow rate by taking an analogy with mass. So the difference between mass and mass flow rate is per unit time. So what is the term which should appear here is a length scale divided by time. So it should be a velocity. So here, this way you can extend the definition, the expression from for the mass to the mass flow rate, that the mass flow rate involves density and surface area, but other than this, it involves a length scale per unit divided by time, which is a velocity. However, notice that surface area is a vector term, velocity is also a vector term. So we take the dot product of these two, and mass flow rate is a scalar term. Similarly, when you take this is the expression for mass flow rate into velocity. This is the momentum flow rate. If you take its x component, this is the x momentum flow rate, this is the y momentum flow rate. I would like to show you the velocity vector. Here the notice that the velocity, this u which has been shown here, is the velocity in the x direction, v is the velocity in the y direction. So I'm showing you here in Cartesian coordinate system. Notice that the variables which you encounter in mass conservation law, mass as well as mass flow rate, both are scalar. So we can call this mass conservation law as a scalar law. Whereas in the momentum conservation law, since this velocity appears, which is a vector term, although mass and mass flow rate both are scalar, the variables which are encountered in momentum conservation law are, since they are vector, so we can call the momentum conservation law as a vector law. So these two terms, mass and momentum, they are directly proportional to their function of volume of the fluid element. They are called as volumetric term. There is the mass flow rate and momentum flow rate. They are function of the surface area, so they are called as flux terms. We are using here a Cartesian coordinate system, and here the expression for the velocity vector is shown. Note that there are two u. The u with the arrow at the top, this is a velocity vector. The u without an arrow, this is a x component of velocity. So the u vector has x component of u vector is denoted here by u. Y component, it's like this is the horizontal velocity and this is the vertical velocity. So there are two terms which are involved while applying the conservation laws in fluid mechanics. So it's like there are two baskets of terms. The first basket, the term which are directly proportional to the volume of the control volume, they are called as volumetric, and the one which are function of surface area are called as flux term. So they are as shown here. Mass, x momentum and y momentum, they are volumetric term. Mass flow rate, x momentum flow rate and y momentum flow rate, they are flux type of variable. If you divide this volumetric terms by volume, and this flux variable with per unit area term. So notice that when I'm dividing this mass by volume, I'm expressing it by m bar. So the over bar represent per unit volume term. This is the expression for, this is symbol for mass. If I use an over bar, it is per unit volume. Mass per unit volume is density. So this is the symbol for density. This is x momentum per unit volume. This is y momentum per unit volume. Similarly, if you divide this mass flow rate by area, this I am expressing by small m, which is a vector. So this is called as mass flux. X momentum flow rate per unit area is denoted here as X momentum flux. Similarly, Y momentum flow rate per unit area is expressed as Y momentum flux. Notice that here I have introduced three types of M. The first, curly M, which I am calling as mass. The second, straight M with a capital letter, this I am calling it mass flow rate. And third, small m, which I am calling it as a mass flux. Notice this nomenclature. This will be used later on in the course. However, note that mass and mass flow rate are scalars and the mass flux is a vector. So if you want to express this mass flow rate in terms of mass flow rate is a dot product of m vector dot surface area vector. X momentum flux is m vector u, y momentum flux is m vector v. So you already know that the mass flow rate, x momentum flow rate and y momentum flow rates are scalar, whereas all these flux terms, they are vectors. You can also notice this volumetric terms, they are scalar, whereas the flux terms are vectors. So finally, the volumetric and flux term in conservation laws are as follows. In a mass conservation law, which is a scalar law, note that the variables which you encounter, the volumetric variable is volumetric mass, which is a density, and the flux term is mass flux. Note that in a scalar law, volumetric term is a scalar and flux term is a vector. In a momentum conservation law, which is a vector law, note that the volumetric term is a vector and the flux term, momentum flux, is a second order tensor. Let me draw your attention to the number of directions which are involved in scalar, vector and second order tensor. Second order tensor, it's like a higher order vector. In a scalar, you do not need any direction. When you define a vector, one direction is involved. When you define second order tensor, two directions are involved. Like when I say here, like this momentum, the direction of this u vector is involved. In case of a second order tensor, the two direction is one direction corresponding to this mass flux, the second direction corresponding to this u vector. So this is a second order tensor. All of you know that whenever you take a dot product of a, let us suppose you have a force F. When you take a dot product with I unit vector, any dot product reduces the vector to a scalar. Similarly, later on I will show you that this second order tensor, because whenever we apply a vector law, we apply component by component. And to take an x component, you will take the x component by taking a dot product with I, and it will reduce the second order tensor to a first order tensor, which is a vector. So as I said, this volumetric term now you see is a vector, and this flux term is a second order, momentum flux is a second order tensor. So in a vector law, volumetric term is a vector while the flux term is a second order tensor. This is shown more clearly through this expression, the two directions which are involved. In a 2D, this M has mx, my, and this U has U vector is involving x component denoted here as U, and this is the y component. This is the horizontal velocity, this is the vertical velocity. And this is the momentum flux. Note that there is no dot or cross product between this M and U. This is called as momentum flux. If you want to obtain its any vector law, whether you have studied in even in statics, dynamics, for solid mechanics, we always apply the vector law component by component. So when we take the dot product, so for x component, while applying the x momentum conservation, we take a dot product and then we get an x momentum flux, where the second order tensor gets converted into a vector as shown here. So the conservation laws are: mass conservation law, rate of change of mass for a fluid element is equals to 0. And the momentum conservation law is rate of change of momentum of fluid element is equals to the force acting on the fluid element. Now I'll show you the two types of variables which are encountered in conservation law. First is the volumetric term, volumetric variable. In this slide, I am showing you variables. In the next slide, I will divide this volumetric variable by volume. I'll call it as a volumetric term. So the volumetric variables are mass, x momentum, and y momentum. And the flux variables are mass flow rate, x momentum flow rate, and y momentum flow rate. Here I am calling this as variables. Now for volumetric, I'll show you a term dividing this term by volume. And if this flux, if it is divided by the surface area, then I'll show you in the next slide as a flux term. So in this slide, I'm showing the two types of terms. So now this volumetric variable, this is mass per unit volume with an over bar. This is mass per unit volume with an, here it says mass per unit volume, which is a density. So this is a volumetric mass. This is a volumetric x momentum. This is a volumetric y momentum. And here it's shown the per unit area term. Mass flow rate is represented by mass flux. Momentum flow rate is represented by momentum flux, which is a second order tensor. And stress, when we apply Newton's second law of motion, rate of change of momentum is equals to force. And force is also depends on the surface area. It's also a flux term. So it leads to a term force per unit area, which is also a stress. When we apply momentum conservation in x direction, we obtain the x component of this second order tensor as sigma dot I, which gets converted into a vector. So I will show you in the next slide. So this slide shows the operation of the second order tensor on momentum flux and the stress for the x momentum and y momentum. Any vector law, as I mentioned, we apply component by component. So here the operation of this second order tensor with a unit vector in the x direction, this is I vector, results you with a vector which is used in the x momentum equations. Note that, as I had mentioned, the second order stresses consist of two directions. The first direction corresponds to the mass flux mx and my. And the second corresponds to the direction of the velocity, which is ui plus vj. In case of stresses, the two directions are represented here by the subscript. There are two subscripts which are shown here. The first subscript, if you consider, let us say, if you consider sigma xx, the first subscript corresponds to the plane, and the second subscript corresponds to the direction in which it is acting. So this stress corresponds to the x plane, which is a vertical plane, and it is acting in x direction, which is a horizontal direction. If on a vertical plane, the stress is acting on a horizontal direction, this is called as normal stress. That is, if you consider sigma xy, this is acting on x plane, which is a vertical plane, but in the y direction. This corresponds to the shear stress. So when you operate, so here, while applying the stresses for x momentum equation, we have to take the x component of the tensor, and this results into, basically, if you operate this second order tensor for x momentum with I vector, you get the first column in a vector form. So you get mx ui plus my uj as shown here. Similarly, when you operate this with I unit vector, you get the first column sigma xxi plus sigma yxj as shown here. Similarly, you can operate this with j, where you will get the second column as a vector for applying this to the y momentum equation. With this, I had come to the end of this topic. These are some of the references for this lecture. Thank you for your attention.